Lab 4, Circuits and Capacitors. So the purpose of this lab was to create a series and RC circuit model using a program called CCK to observe the behavior and to measure the resistance, voltage, and current across the whole circuit. The first goal was to predict and calculate how these behaviors act numerically, and then to compare our results with the computer program CCK. And the second goal was to model a series in CCK to determine its change in potential energy. And the last goal was to model an RC circuit and then create a plot to compute the RC time constant of the circuit. So the fundamental principles was Ohm's law, loop rule, and node rule. Loop rule stating that the current going in is equal to the current going out, and node rule where the sum of the currents flowing into that junction is equal to the sum of the currents flowing out of that junction. So for series circuit model 1, I got that the readings from the CCK ammeter, 0.02 amps, was approximately equal to the one that I predicted, 0.0204 amps, as shown in these two diagrams right here. And then for series circuit model 2, I broke up the circuit wire, and then I measured the voltage across with a voltmeter, and I got a reading of 3 volts. And the voltmeter measures the potential difference of the circuit, and it's positive because the red probe is placed at a location with a higher potential difference than the black probe. And the ammeter reads 0 amps because since the wire is broken, there's no current going across, so therefore it would have 0 current. So for series circuit model 2, I measured the current across all these points. So across AB, I got a reading of 3 volts. Across CD, I got a value of negative 0.95. And then across EF, I got a value of negative 2.041. And the voltage of the brown strip is, when all summed up, it equals 0, which is just how I predicted up here. So the potential versus the position plot. So the ammeter reading does not change when I attach the voltmeter because an ideal voltmeter has infinite resistance, therefore the current remains the same. So it starts off at 0, and then it accounts for the 2 batteries, summing up to 3 volts. And then from B to C, it's 0, drops down by this amount, and then it's from D to E, it's constant again. And then from E to F, it drops down by this, and then it reaches an equilibrium of 0 down here. So for circuit model 4 with the parallel ammeter, so the current that I got for this was 0.06 amps. So the current increased from 0.02 amps to 0.06 amps. And this is because the current no longer travels through the 100 ohm resistor. Instead, it goes around using the 2 new wires, these two, and passes through this new ammeter. Therefore, only the 47 ohm resistor has an effect on the current. So resistance results. For the 47 ohm resistor, I got this value. The 100 ohm resistor, I got this. And then for the wire and the ammeter, I got 0 ohms. And then RC circuit model 1. So when I connect the battery, the light bulb, and the capacitor, the light bulb lights up for a couple of seconds, and it quickly dims down, and the capacitor develops a charge. And then when I discharge the capacitor, the light bulb lights up for a couple of seconds, and it quickly dims down, and the current travel in the opposite direction. So the 10 ohm bulb charged in the capacitor charged in about 20 seconds and discharged in about 19 seconds. The 20 ohm bulb charged in about 44 seconds and it discharged in about 38 seconds. These are pretty rough estimates. And then this is my plot for the natural log of the voltage versus a time. So it is a linear relationship. Here is my time, voltage, and then the natural log. And then the slope, as said in the instruction, was -1 over RC, and the slope of the line was negative. The slope of this line turned out to be -0.186. And then when I compute this for the RC time constant, I got a value of 5.38 seconds. So the conclusion. The loop rule was proven by measuring areas with non-zero potential differences and adding them all up to 0 volts round trip. The potential versus the position plot visualize how the potential increased to a maximum of 3 volts and decreased back down to an equilibrium of 0 volts, satisfying the loop rule. The time constant I calculated was 5.38 seconds, which was just off from the RC value of the CCK. The ammeter readings do not change when I attach the voltmeter because an ideal voltmeter has an infinite resistance, therefore the current remains the same. Follow-up questions. So if I was doing this in real life, an ideal ammeter has 0 internal resistance, so therefore it wouldn't drop voltage as current flows across, whereas actual ammeters have some resistance which has an effect on the current flowing across, and a simulated ammeter would have a higher reading than the actual ammeter. And if I was doing this in real life with a real battery and a real capacitor, an ideal battery and a capacitor have no resistance. Therefore, it showed that the capacitor would fully charge instantly right away. And real life batteries and capacitors have some internal resistance, just how actual ammeters do, which would slow the charging of the capacitor.